if people want their way in. I'm going to give about a half an hour to a 35-minute lecture today, and then we're going to do the CUE guide forms. So last time we showed, if we had a ring R, that we had the following implications. This is a domain. That R is Euclidean, which meant we had a size function, R minus 0 to the positive integers, so that you could do a division. Could always do a division of B by A so that delta R was less than delta of A, so that we had a Euclidean algorithm in the ring. That implied that every ideal I in R is principal, and in fact was generated by an element in it of minimal delta, and that implied that every element in R had a unique prime factorization, namely could be written as an element in R, A, could be written as a unit times a product of elements in R where these are prime elements, primes in R, this was a unit, and that this factorization was unique up to multiplication of these primes by units, so that the element A determined these prime factors. So remember that an element is prime, P in R is prime, if and only if the principal ideal generated by P is a non-unit ideal, so it's a non-trivial ideal, it's not equal to R, but is maximal with respect to principal ideals. Namely, there's no factorization of it, P is equal to AB, where either A or B generate a larger ideal than P. Either they generate the same ideal at P or they generate the unit ideal. So it's maximal with respect to principal ideals, so that any element has a unique factorization into primes, just like in the integers. And we proved that a number of rings were Euclidean and consequently had all these properties. So the examples of Euclidean rings, of course, the integers, that's where it started. We showed that polynomials over a field were Euclidean, where this function was the degree of the polynomial. And then we showed at the end that the Gaussian integers were Euclidean, so every ideal is principal, and we had this factorization. Next time, we're going to look more closely at what are the primes in the Gaussian integers. When you have this theorem, it's only valuable if you really know what the primes look like. So in this ring, they're the usual prime numbers. In this ring, they're what we call irreducible polynomials. Here is prime, here it's an irreducible polynomial. And next time, we're going to find out what the primes look like in the Gaussian integers. But we did these implications. And then at the end of the lecture, I gave an example of a ring which did not have these two properties. Namely, first of all, the ideals were not necessarily principal, and that implied that R wasn't Euclidean. And the example of a ring, so this is another way of stating this, by the way, is that R modulo P is an integral domain. Because that would say if you had a product in here that was 0 and a product that was in here that was 0, you'd have something like A bar times B bar is congruent to 0 mod P. That would mean that either P had to divide A or P had to divide B. Namely, there were no non-trivial factorizations of it, which would mean that either A bar was 0 or B bar was 0. So a prime element is 1 such that when you mod out by the principal ideal, you get an integral domain. Now, the way we showed that there were ideals that were not principal was if this ring is not a field, then there are non-principal ideals. So let's make an observation. If R mod P is not a field, then there exists an ideal I which is lying between P and R. So if you can find a prime element so that this is a domain but is not a field, that means that this quotient ring has more than two ideals, right? We proved the field was one where it had only two ideals, 0 and the whole ring. If remember about the isomorphism theorem, the ideals of this ring are exactly the ideals of R that contain P. So there has to be a non-trivial ideal that lies between P and R that creates a non-trivial ideal in this quotient ring, if it's not a field. Now that ideal can't be principal, because by the definition of being prime, this thing is maximal with respect to principal ideals. Nothing contains it that's an actual principal ideal, because that would give a factorization. So if you're in the situation where you're able to identify one of these quotients by a principal ideal, which is a domain but not a field, then you cannot have this property that every ideal is principal. Okay? And we gave an example of this. Example where the ring was polynomials over the integers and where the prime was x, and then R modulo the ideal generated by x we showed was isomorphic to z, and that's a domain but not a field. And I gave an example of an ideal I that contained P, namely you take the ideal generated by x and a prime number like 2 that contains the ideal P, but it's not equal to R because it's the kernel of the homomorphism that takes an arbitrary integral polynomial, takes its value at 0 mod 2. So this is the map. R goes to z mod 2 that takes f of x to f of 0 mod 2. Namely, it takes it to the mod 2 reduction of its constant term. And there are polynomials like f of x equal 1 that is not in this ideal. Okay? So we gave an example of a ring here, which was certainly not a principal ideal ring, because it had a non-trivial ideal which wasn't principal, and consequently could not have a Euclidean algorithm. But at the end of the lecture, I told you that in fact it does still have unique factorization, that this is a weaker condition than either of these two. So I want to show you that to you today because that's a really great result of Gauss's, and it's what we use to factor polynomials even over the rationals. So that's what I'm going to show you today. In fact, even though z of x is not a principal ideal domain, it has unique factorization. And we'll say what the primes are and everything. And the more general theorem, which you can find in the book, which I'm not going to show it to you, which is the thing you can get out of this method, is usually stated the following way. In fact, if R is a domain with unique factorization, into primes, so is the ring of polynomials over R. You see, Z has unique factorization. So we're going to see the polynomials over Z also have unique factorization. So in particular, if you know this extra theorem, that implies not just polynomials in one variable, but polynomials in two variables over Z have unique factorization. Because once we prove that this has unique factorization, if we take polynomials over this ring, then we get polynomials in two variables. Or polynomials in n variables over a field. x1, x2, xn has unique factorization because polynomials in one variable over a field have unique factorization. And then you take polynomials over that in another variable, and that has unique factorization. Okay? So it gives an inductive way of proving that things have unique factorization, whereas we don't have an inductive way of proving that things preserve principal ideals. Certainly not the case that if you adjoin a variable, you still have every ideal principal. Okay, so now let's talk about factorization in integral polynomials, because that's the subject today. This was all sort of background to the lecture. Now, you see, if we start off with a polynomial with integer coefficients, this is a subring of the polynomials with rational coefficients. And the rational numbers are a field. So if we forget that we're in this subring and we just look at the element here, we can certainly factor it into irreducible polynomials. So we do that. We write it as a unit times p1 of x, pk of x, a factorization in q of x. So these polynomials are monic, irreducible polynomials in q of x. There's no problem with that. We just think of ourselves in this larger ring that has unique factorization. And this is a unit which is a non-zero rational number. And that factorization is completely unique because this is so this ring is a principal ideal domain. It's a Euclidean algorithm domain, so it has unique factorization. The problem is that, first of all, this rational number might not be in this ring if it's not an integer. And secondly, there's no reason that these monic polynomials in the factorization have integral coefficients. So for example, if I took a stupid polynomial like 2x plus 1, which is a perfectly nice polynomial with integer coefficients, right? And I wanted to write it in this unique factored form, I would write it as 1/2 x plus 2. Oops, sorry. Let's try that again. 2, there we go. 2 times x plus 1/2. Excellent. Because here I have to have a monic polynomial. Now that's irreducible because it has degree 1. Here would be my c. That looks pretty good. But this isn't good at all. This isn't an element in z of x. So the problem is these factors not be in z of x. And this itself is an irreducible element. This is a prime element in z of x, it turns out. And the problem is that it's not monic. You can't make it monic and stay in z of x. So what we need to do is somehow have a replacement of the notion of a monic polynomial that allows us to do some factorization like this, but to ensure that these things are actually have integral coefficients. So the analog of a monic polynomial in z of x is what's called a primitive polynomial. So a primitive polynomial, I'll call those things like f0, has the following form. So the coefficients are all integers. And primitive means you can't divide by anything. So they're not all multiples of anything. Like this is a primitive polynomial because it has a coefficient which is 1, so you can't divide anything out of this. So what primitive means is that the greatest common divisor of all the coefficients is 1. In other words, that the ideal generated by the coefficients, that's another way of saying it, in the integers, the ideal generated by that is all of the integers. Ideal generated by coefficients. Because if the ideal were smaller, that would mean that there was some number that divided all the coefficients and you could divide out. Now, if you think of this condition, you could still preserve that condition if you multiplied the polynomial by -1. So if I took this polynomial and I wrote it as -1 times -2x minus 1, this would still look like a primitive polynomial. Right? So I don't even want to allow myself to do that, to multiply by -1. So the final condition I do to make my primitive polynomials as unique as possible is I assume that the highest coefficient, which is non-zero, is actually positive. Sometimes that's not assumed, but the way Artin does it, and I think it's a nice way, you assume that there are no common divisors of the coefficients and that the highest coefficient is positive. All right? Then I claim that any polynomial over the integers can be written uniquely as an integer times a primitive polynomial, where this is an integer. And this is unique. Well, that's more or less obvious, isn't it? I mean, I just see what the greatest common divisor is. I pull that out. That's going to be my initial choice for C. But then the problem is that this thing might not have a positive coefficient. So if it doesn't have a positive coefficient, I multiply that C by -1. So that's my C. And then I'm left with a primitive polynomial. And then there's nothing more I can do. I can't pull out anything of this because it has GCD1, and I can't multiply it by any integer because that would either create a GCD or it would change the sign of the first coefficient. So this is already primitive, but if I had a polynomial like 6x squared minus 3x plus 9, then that would be written as 3 times 2x squared minus x plus 3. And this would be the C, and this would be the f0. Because all these coefficients were divisible by 3. Okay? Now, what's cool about this, what's particularly cool about it, is that not only do I have such an expression for an integer polynomial, I have it for a rational polynomial. And that's very interesting. In fact, if f of x has rational coefficients, then you can write f of x as c times f0 of x, where this is primitive in z of x, and this is a rational number, and this expression is unique. So that any rational polynomial determines a primitive integral polynomial and a rational number, just like any integer polynomial determines an integer and a primitive polynomial. So let's see how that works. I just start with my rational polynomial. That has only finitely many coefficients. Each coefficient has only finitely many denominators in it. So there's an integer that I can multiply f of x by a large integer, n, so that n times its coefficients are integers for all I. So n times f of x is in z of x. Okay? And then I write that uniquely as d times f0 of x, where d is an integer and f0 is primitive polynomial. And then I've got an f of x written as d over n times f0 of x. So it's written as a rational number times a primitive polynomial. Okay? And then the only thing you have to do is check that this is unique. It's more or less obvious it's unique. I'll let you take a look at the proof of the book that it's a unique decomposition. But I mean, it's more or less clear that what we get here, f of 0, is unique, because if we multiplied by a bigger n, we would just pull that amount out of f0. Okay? Now, what's cool about this, and this is very important as we're going to see, is that you can tell from this decomposition when your polynomial is integral and when it isn't. And that's part of the unicity. In fact, f of x is in z of x if and only if this constant is in z. This constant, by the way, is called the content. That's an expression of Gauss's. We're just redoing some of Gauss's work on polynomials. So you take any rational polynomial, you write it as a rational number times a primitive polynomial, and then you find that the polynomial is integral if and only if that constant is an integer. Well, let's see why. If the polynomial is integral, then it's clear the constant is an integer. You just divide out by the greatest common divisor of all the coefficients. So that part is easy. Now, on the other hand, if the content is an integer, then this expression is an integer polynomial. Okay, so we just did it. Okay. Okay, now, here's how I'm going to do this factorization in Z. Very cool. I take this factorization in the rational numbers, and I replace all these irreducible monic polynomials by their primitive parts. So I write this as C times C1, P1, I'm calling it 0. Let's call it Q1 of x times C2, Q2 of x times CK, QK of x. So I rewrite that as D, which is the product of the C's and all the C1 through CK, times Q1 of x, QK of x, where these are now primitive polynomials which are irreducible in Q of x, because they're just scalar multiples of these irreducible monic polynomials. So each monic polynomial I write as a constant times a primitive polynomial, just like I did for that example, this 2x plus 1, which I've written as 2 times x plus a half. I would have started by this x plus a half and written it as a half times 2x plus 1. So this would be a typical conversion. If P1 were x plus a half, I'd write it as a half times 2x plus 1. So I pull out these rational numbers, C1, C2, CK. I pull them all into the constant D, which is C times C1, C2, up to CK. And then I'm left with primitive integral polynomials, which themselves are irreducible in Q of x. Yeah? In fact, okay. I claim that when I write the polynomial this way, that the polynomial has integral coefficients if and only if this constant is an integer. Okay? If the constant is an integer, this has got integer coefficients. So if you multiply a polynomial of integer coefficients by an integer, you get an integral polynomial. Okay, so that's this direction. If the polynomial has integral coefficients, right, then we saw that it could be written as an integer times a primitive polynomial by taking this integer, which is the greatest common divisor of its coefficients. Since this expression is unique, that shows that if you start with something integral coefficients, you get an integral content. So that's why you can tell whether your polynomial has integral coefficients just by looking at its content in this factorization. Yeah?
Why do we have a field where it's guaranteed
No, I didn't say it was an integer. Oh, absolutely right. It's in Q. No, absolutely right. First of all, this could have been in Q. Secondly, all of these could have been in Q. So far what we've got is we've shown that any integral polynomial can be written as a rational number times a product of primitive polynomials which are irreducible as rational coefficients. We're getting there. We're not there yet. By the way, I'm going to show you that this is an integer, but I haven't done it yet. So far, we're just here. Good point. Okay, now here's Gauss's great lemma. Gauss has a lot of very famous lemmas. There's another Gauss lemma that goes into the proof of quadratic reciprocity. But here's his lemma on polynomials. If f0 and g0 are primitive polynomials, so is their product, f0 times g0. So in particular, this product is going to be a primitive polynomial because it's the product of primitive polynomials. Now, because I don't want to leave you hanging, I'll show you that this is an integer. Because I've written f of x as a rational number times a primitive polynomial. But that expression is unique, and f of x is an integral polynomial. Therefore, this has to be an integer. Brilliant, huh? But you see, I have to, knowing that each one of these is primitive is not enough. I have to somehow know that their product is primitive. So that's Gauss's lemma. Now watch how this goes. This is absolutely wonderful. Proof. If not, say the prime p divides all the coefficients of f of x times f0 of x times g0 of x. That's what happens when you don't have a primitive polynomial. The GCD is not 1. So some prime divides the GCD. So some prime divides all the coefficients. Okay? Now consider the homomorphism. The ring homomorphism that takes polynomials with integer coefficients to polynomials with coefficients mod p. That takes a polynomial, well, it takes an integer n, a, goes to a mod p, and it takes x to x. So it just reduces the coefficients mod p. It takes a polynomial summation of an x to the n goes to summation of an bar x to the n, where this is the coefficient mod p. That's a homomorphism, because I told you what it does on the integers, and I told you what it does on the generator, and then you just extend multiplicatively. That says, if a prime divides all the coefficients of this, that says that the image of this polynomial under this homomorphism is 0. Okay? Which means, because this is a ring homomorphism, that the product of f0 bar and g0 bar is 0, because the image of the product is the product of the images. Okay. Now what's wrong with that? Why? Because this ring is polynomials over a field. Remember, Z mod p is a field. So this is an integral domain. And here we have the product of two elements is 0. So that implies that either f0 bar equals 0 or g0 bar equals 0. And that contradicts the fact that these polynomials are primitive, so that no prime divides all their coefficients. So this is a really great argument in Gauss. Of course, it was before there were rings and homomorphisms or anything like that, so he had to do it from complete scratch. Okay? So that's Gauss's lemma. And that tells us we're almost done here. That tells us that now we have a factorization where, since this is primitive, this is actually an integer. And now I'm going to show you another cool thing that Gauss discovered, which is that these polynomials, well, if they're irreducible in Q of x, they're also irreducible in Z of x. Right? I mean, if I could factor them in the integers, I could have certainly factored them in the rational numbers. Right? So that these things cannot be factored any further in the integers, so they're prime elements of the integers. So to obtain a prime factorization, all I have to do is further factor this integer, which I do into normal primes. So I write that now as plus or minus p1, p2. These are normal integer primes, pl, times q1 of x, qk of x, where these are integer primes, which are certainly prime in z of x. And these are primitive, irreducible polynomials in z of x. And this is a decomposition of an arbitrary polynomial into prime elements in z of x. And a little more work, not too much, which I'm not going to do here, but you can read in the book, will show you that this decomposition is unique, and that's the factorization. Any integer polynomial determines first a set of primes which divide its content, which is the prime factorization of the content. Factorization of the content of f of x. And then it determines a bunch of irreducible primitive polynomials, which in some sense correspond in a one-to-one way to the monic factors of its factorization in the rational numbers, and you've just sort of cleared out their denominators and made them primitive. They have the same degrees, etc. So the factorization looks very similar to what it does in the rational numbers, except you pull out this integer content, and that's the completion of it. Now, you may say, well, why worry about factorization in z of x at all? And the reason it's easier to prove polynomials in z of x are irreducible than in q of x. And it turns out there's another thing that the polynomial's irreducible in z of x if and only if it's irreducible in q of x. And the reason it's easier to prove that polynomials are irreducible is because we have the benefit of this homomorphism. You see, if you have a homomorphism like this, and you want to test, is something in here irreducible, you can take its image in here. If you can't factor the image in here, you certainly couldn't have factored the image in here. Namely, if you have some polynomial here that you want to study, and you have it factored as m times n, then when you take f bar, that's m of x times n bar. These have the same degree as m and n, assuming you've done some factorization where the highest coefficient isn't divisible by p. And so if you didn't have any factorization in this ring, then you couldn't have had a factorization here, and it would have been irreducible here. And here it's easy to check whether things are irreducible because you only have finitely many polynomials of each degree to try. So if I have a polynomial of degree 4 with coefficients in the field of 2 elements, I only have to see whether it's divisible by things of degree 1, 2, and 3. And I can list the polynomials of degree 1, 2, and 3 over the field of 2 elements because their coefficients are just 0 or 1. Whereas I can't list the polynomials up to degree 4 in here, let alone in the rational numbers. So a polynomial of degree 4, I might have trouble factoring the rational numbers. But if I multiply it by an integer, get it to the integers, and then I reduce it modulo a prime, and I discover that it's irreducible there, then it was irreducible back here. So it's easier to prove polynomials irreducible in z of x as you can check irreducibility in some image. And you can't map q of x to this because p is not a prime of q of x, but you can map z of x to it. So I'll give you one example of that. Example. And the book does many others. Let's see if I can find a good one. Oh, I don't seem to have a good example. Oh, I don't know. Let's take x cubed plus x plus 1. That's f of x. Is irreducible. Proof. Look at the image in z mod 2 of x. Does it have it factor f of x is, say, m of x times n of x? Well, this is of degree 3. If I had a non-trivial factorization, one of these things would have degree 1, one would have degree 2. Okay? I mean, they have to add up to degree 3. So if it factored in z mod 2 of x, one of these would be of degree 1, so it would look like x plus a, and then it would be x squared plus bx plus c. Okay? Which would mean that I'd have a root of the polynomial in the field of 2 elements. So then f of minus a is equal to 0 in z mod 2. So if you had a factorization, you would have had a root. But it's easy to check that this polynomial has no roots over the field of 2 elements because there are only 2 things in the field of 2 elements, 0 and 1. If you put in 0, f of 0 is 1. And if you put in 1, f of 1 is 1 plus 1 plus 1, which is 1. So this doesn't happen. Therefore, there's no factorization. Now you might say, well, what about a polynomial of degree 4? Yeah, what about a polynomial of degree 4? I don't know. Let's try a polynomial of degree 4 and see if I can hack it. I could try this, x to the 4th plus x cubed plus 1. Let's hope that that's irreducible. Well, we could look at the image in Z mod 2 of x. It certainly doesn't factor as a degree 1 times a degree 3, because again, it has no roots. 0 and 1 are not roots. On the other hand, maybe it factors as a degree 2 times a degree 2. Okay? So, again, these degree 2 have to be irreducible because I have no roots. So I just have to look at what are the possible irreducible polynomials of degree 2 over the field of 2 elements. And there's only one of them. The only irreducible polynomial of degree 2 over the field of 2 elements is this, because you have to write down something without any roots. So the only question is, does this polynomial divide this polynomial? The answer is no, because the only possibilities, if it divided it, you'd be left with something else of degree 2. So the only possibility is you'd have to square this polynomial, right? But the square of this polynomial is not equal to that polynomial. The square of this polynomial is, in fact, x to the 4th plus x squared plus 1. So it's not equal to this. So this is irreducible in Z of x. Please.
How come there can be another polynomial of degree 2 other than x squared plus x plus 1?
Because any other polynomial of degree 2 would have a linear factor. Let's look at the polynomials of degree 2, Atticus, so that you see what I mean. This is irreducible of degree 2. The other polynomials of degree 2 would look like x squared plus 1 and x squared plus x. Those are the only two, right? Or just x squared. Those are the 4 polynomials of degree 2 because it has to start off with the coefficient 1. So you have a choice of 0 or 1 here or 0 or 1 here. That's it. This clearly has a root, x equals 0. This clearly has a root, x equal 1. And this has a root, x equals 0 and x equal 1. So they're not irreducible. So if I factored, we already agreed it had no linear factors, so if it's split 2 and 2, these would both have to be irreducible of degree 2. Because if they had a factor, it would have a factor of degree 1, and we agreed this polynomial had no factors of degree 1. You get the hang of this? So it becomes extremely useful to use this moving to the integer polynomial and the content and everything if you want to study factorization even in the rational numbers. You test factorization in the integers, and to test factorization over the integers, you check factorization modulo a sufficiently well-chosen prime p. Now I have to warn you about something that's very amusing. There can be polynomials which are irreducible over the integers, but for every prime p factor. Artin gives an example of that. That was slightly annoying. Yes?
So what does happen when the coefficient is a number that you're monifying?
If you're not factoring a monic polynomial, you have to stay away from primes that divide the leading coefficient. That's all. And that's almost all primes. See, this argument that when you reduce a polynomial and you get a factorization, the factors have the same degree, is based on the fact that the leading coefficient of this polynomial is not divisible by p. So any given polynomial that you're studying with coefficients in the integers, the leading coefficient is only divisible by a finite number of primes p. Throw them away and use the other primes to test irreducibility. Okay? Good question. Because we don't necessarily have monic polynomials. So Peter and I have assigned a number of factoring exercises for you. This is an important part of the theory, and it's very useful in practical computations. It's extremely useful in coding theory, for example. Those of you who go on and work in coding theory will learn. It's very useful to construct polynomials, say, over the field of 2 elements that are irreducible and have large degree. One of the leading conjectures that's never been proved is that, first of all, it's known that there's an irreducible polynomial of every degree. That's not obvious, right? I mean, we just got lucky in quadratic polynomials. There was just one that was irreducible. But it's known from the theory of fields there's an irreducible f of x of any degree. What would be very useful in coding theory is to prove that you could always make an f of x that looked like this. A trinomial, namely with only 2 other coefficients. Is there an irreducible trinomial of every degree over the field of 2 elements? People have checked it, I don't know, up to degree 10,000, maybe 100,000. I don't know what the current rate of computation is. No one can prove there's always an irreducible trinomial. From the point of view of coding theory and making computations of sequences, this would make life a lot easier. Actually, it would look like this, because the non-zero coefficients in the field of two elements are just 0 and 1. So this is just the beginning of a fabulous theory, but I want to do a little bit more on the Gaussian integers and about integers in quadratic fields. So I'm going to stop with polynomials here. That doesn't mean you should stop with polynomials here, but I'm going to stop in this course. When you take 123, you're going to learn all about Galois theory, and Galois theory is just the study of polynomials in one variable with coefficients in the integers. That's it. That's a good way of saying it. But what I'm going to ask you to do now, if you can, is to take the rest of the class to fill out the CUE guide. So I discipline professors vigilantly on the basis of their low scores on the CUE guide. So I don't want you to have me discipline myself. That would be very bad. I'll ask you to pass them out, and while you pass them out, I'm going to make a little announcement. So you're supposed to fill out, who's Professor A, who's section leader A, etc. So I am Professor A on this form. You should use a pencil if possible. If not, a black pen. Do not use red ink. So Professor A happens to be me, and your section leader happens to be Peter Green. That's on the back. We don't evaluate the TAs, even though they've done a fabulous job. So please take the rest of the class to take time. I really do use these things enormously. I'm going to probably give this next year if I maintain my sanity until that point. And I would like to get your comments on the material covered, the speed, the appropriateness of it, whether you got anything out of this. I can take it. I can take it. Believe me, it would help me. And I also need a volunteer who at the end of the class will collect these and take them back to University Hall, because I'm not supposed to touch them anymore. And neither is Peter. Does anyone have a chance to go back to University Hall later today and can collect them? Thanks. Thanks. First floor of University Hall.